Let's move to the second speaker. So, second speaker is Urgench from Korea, in UNIST. So, the Professor Park will be talking about real-time quantum dynamics of condensed matter, nonlinear physical properties, and very cultural parameters. So, after Professor Park's talks, we have, as announced, we have a short coffee break for 10 minutes. Let's welcome the Professor Park.
Okay, hello, I'm Urgench from Korea. Let me first thank all organizers for inviting me for this nice chance of a presentation and a beautiful place. So, microphone is okay? Yeah. Okay. I will talk on the kind of so it doesn't work. Okay. I wrote the title, the real-time dynamics, but let me explain you a little bit later. I came from Korea, and my place is something southern eastern part, and you know the very southern eastern part, and the UNIST is a kind of a national institute, and we have so let me emphasize that to your student members, we have many students, especially many foreign students, and also we have many, Central Asia, Stan, Uzbekistan, Kyrgyzstan, Kazakhstan. We have many students, so that you may think of applying the graduate study in our institute. So this is our home page. Today, this is the content I plan to present today shortly. Let me shortly summarize what we are doing in our laboratory, and let me shortly and very introductory manner summarize the Berry phase, something about the Berry phase and Berry culture. In the context of a response theory, and let me summarize our work for something related to the optical response, non-linear optical response of nanomaterial. So let me begin. So I have been developing, and I'm planning to extend this type of time-dependent time-dependent density functional equation by combining the material DFT Hamiltonian with the light field. Let's say that I want to develop something with the light matter hybrid within the ab initio manner. And by developing this method of a package, we want to develop kind of the structures of response theory. When it comes to response or measurement of experimental physicists, we always perturb the system by some manner, and we measure the response. So in this kind of measurement and data collection, the perturbation might be strong or weak, and the response could be belong to linear response or non-linear response. We want to develop our data all these perspectives, to cover all these perspectives. By doing this time-dependent simulation, including the light field, especially the dipole approximated uniform applied electric field in the momentum operator and also the scalar operator. So for example, once we have the time evolving wave function or specifically Coulomb orbital, we may calculate the charge current this way by taking the expectation value, or we may current the spin current, or some others like orbital flows and something like that. By calculating this one, we will apply the response of material character. For example, this is one example of the quantum spin Hall, two-dimensional topological insulator, and by performing the real-time dynamics, the psi t you see here, real-time dynamics, we can calculate the quantized spin Hall conductivity as you see here, the real-time and the quantized spin Hall conductivity. So we analyze the material property, for example, the topological insulator, by doing the real-time calculations, something like that. And so in this perspective, we have worked many light matter hybrid, and so for example, let me say that the material under a strong light, and this is something like I owe greatly all this development to my great collaborator, so the Max Planck persons and our members. Some of our members, students, are now start as professors in Korean University, and other collaborators in Israel and in Chunghwa University. So the overall, we want to develop that in the condensed matter side, the faster phenomena, which might be bridged to the optics side, the nonlinear optics. So that I want to kind of say that the faster dynamics of condensed matter, they can be bridged with the nonlinear optical phenomena. This is what we are doing, what we plan to do, and. So, in order to discuss something about the response character, let me shortly summarize the very phase. Maybe some of you or many of you are physics majors. So let us please remind you. Let us reflect and remember some quantum mechanics textbook, undergraduate quantum mechanics textbook. In any of undergraduate quantum mechanics textbook, you might have solved this problem, the most simplified problem, a particle in a one-dimensional infinite box. The solution can be easily solved, and the eigenfunction, we have the eigenfunction and the eigenvalue. Normal mathematics, exactly the same mathematics can be duplicated to achieve the particle in a three-dimensional box. So let's say that this one. This is the eigenfunction of the ground state, and this is the ground state energy eigenvalue. So let's say that the single particle problem in quantum mechanics is something easy to obtain the eigenvalue and the eigenfunction. But our quantum mechanics, please remember that our quantum mechanics never determines the overall phase. So actually, the eigenfunction is something like there is the undetermined phase. So the quantum mechanics has no reason, no way to determine this phase. Then let me suggest that this problem. We have a particle in a box, but let's say that this particle is somehow the electron, proton, or charged particle in a box. And let's move the box very slowly, move some other place. Then this moved state of a particle, in the adiabatic limit, it preserved its wave function shape, but the only coordinate is just translated. This is the adiabatic translation of the wave function. I think it makes sense in your mind. And let me suggest a very interesting problem that was actually first presented by the Professor Michael Victor Berry. Suppose we have a very thin solenoid here, very thin solenoid, and so it has spatially confined magnetic flux. And let's move our particle in a box. One way that avoiding the solenoid, and the other way surrounding the solenoid. What Barry speculated, what Barry suggested is that these two situations, even though the particle completely come back to its original position, one way surrounding the solenoid, the other way avoiding the solenoid, these two situations will result in completely different state. What is different? The thing is that the Barry phase. You know, Michael Barry more specifically wanted to compare that the time-independent Schrödinger equation and the time-dependent Schrödinger equation. And the question is that when you start from a specifically well-defined state and time evolve and the Hamiltonian changes through a parameter RT, what will be the time-dependent wave function at time t? This is the original, his paper 1984, and Michael Barry suggests that the time-dependent Schrödinger equation, the wave function, time-evolving wave function, and the time-independent eigenstate, these two wave functions are very beautifully, very well correlated. Besides, there is additional phase. This is called the Barry phase. And another very interesting, great mystery of quantum mechanics is that one thing summarized in the Stephen Weinberg lecture note that this Michael Barry's interesting cartoon suggests that actually the Barry phase in this example is exactly the same as Aronoff Bohm phase, and even in this Stephen Weinberg lecture note that by some coordinate transformation, the Aronoff Bohm phase can be equated with the Barry phase, so the Barry phase might be the wider concept. Anyway. So as we have a Barry phase, we can think of a gauge potential that is the Barry connection, which is gauge dependent quantity. But by differentiating the gauge potential, we will obtain the Barry curvature, which is a local intrinsic measurable quantity. Very curvature. So the thing is that not only the eigenvalue, we have something important, something significant quantity can be derived, the eigenfunction, which is the Barry connection. In the solid state physicists, the thing is that the parameter R becomes the flow vector K, so that we have an intrinsic Barry curvature for the solid state itself. This is the physical quantity. Now we defined in terms of the Michael Barry's context, the Barry phase, Barry connection, Barry curvature. Let me come back to the response theory. We apply some perturbation and we observe the system's response, and so especially for example, we have suppose we have some material and we applied some driving optical drive or static drive or anything. We apply some drive or applied bias. For example, let's say we apply the bias in the x direction, and we want to measure the response of the system. For example, apply the x direction bias and let's measure some y direction response or something, the off-diagonal response. There is a systematic theory to calculate this response, or something, perturbation theory in the interaction pictures or something like that. And anyway, let's say that we can calculate the response this way, and the first order response that is linear to the drive. The first order response can be written this way, can be derived from the Khiva formula. And first order response, the response coefficient is very curvature. So we can summarize that the very curvature is the off-diagonal linear response intrinsic coefficient. And to every transport experimentalist, the presence of very curvature can be very well measured by the whole component of current, the whole velocity. So this is the manifestation of the solid state very curvature. The off-diagonal response, X bias of the response in perpendicular direction. But the thing becomes more important at the time of 1982. The very famous paper TKNN, they found that the band insulator hole conductivity that came from the presence of a very curvature is they understood that they revealed that the hole conductivity is quantized. So the mathematics tells that the quantized hole conductivity is proportional to the total summation of a very curvature. So this summation of a very curvature serves as a topological invariant. Topological means that even though the Hamiltonian or the system might be gradually changing, but somehow its gap doesn't collapse, that the total summation of this very curvature is invariant, it becomes a constant. So this is a kind of a starting point of integer quantum Hall or the topological characterization of the material. And you know the topology, mathematical concept of a topology originated from the German mathematician Euler, the 18th century Switzerland mathematician Euler. And you see that some kind of this tetrahedron, octahedron, icosahedron, the outer shape is changing, but there is, we can think of something invariant. This is a topological number. In a modern sense, in a modern sense, you know, when you play molding the clay, something remains invariant. For example, this left side family and this right side family can be characterized by the total integration of a Gaussian curvature. So even though this overall the various shape, total integration of a Gaussian curvature remains something constant. So in quantum mechanics or solid state itself, even though the Hamiltonian might vary somewhat, but the total integrated very curvature remains constant. This is a kind of the topological characterization of the material property. And so let me go over to the nonlinear optical response of the system. You know, up to now, I introduced the very curvature, the linear octagonal response character, integrated the very curvature as a choice number, topological invariant. Now let's discuss something of the nonlinear response, especially let me discuss the second order optical response. And especially when it comes to the second order optical response of the monochromatic driver, single frequency driver, our second order response must have something, two components. One is a DC response. This is the omega minus omega. So this is a zero frequency DC response. And the other is omega plus omega, 2 omega second harmonic response. Let's say that the second harmonic response can be grouped in two families, DC response, second harmonic response. And in the optical response, DC response can be grouped in the shift current, which is response to linear current, non-linear response to linear driver, not circular. Non-linear response to linear driver, and the injection current, which is the response to the circular driver, something like that. And we and other collaborators have been discussed that this second order response is proportional, is characterized. Please remember that the first order response and the topology was characterized by the very curvature. Second order response will be characterized by the very curvature dipole. The thing is that this one. And the famous paper is that in 1915, Liang Hu showed that in the one-band metallic system, the DC response and the 2 omega response, which are the second order response, it will be very well characterized. The character big D is very close dipole. But we are more interested in the insulators, nonlinear optical response, and specifically we are interested in the second order optical current of some materials. And recently we have studied some nanostructures, for example, TMDC nanotube, and we studied the second order photocurrent, which is the DC response to the linearly polarized light of the second order DC response, which is the shift. And among the investigated nanotube, the zigzag type, it depends on the wrapping angle, but the zigzag type of the TMDC nanotube has very interesting, it has the polarity, but this is the calculation of the shift current, but we found that the double wall or multi-wall nanotube have very efficient, very extraordinary, very significant increase in the shift current, the response, the second order photocurrent, in response to linear response, because of the presence of interwall charge shift. Interwall charge shift provides a significantly increased second order nonlinear response photocurrent. And we investigated the reason, and so we provide something Janus type of some hypothetical model, Janus type of double wall nanotube, even result in the even bigger shift. So let me shortly summarize my talk. That we are working and we have been developing the real-time, time-dependent DFT calculation by fully taking into account the effect of a light field or any other driver. And by doing this simulation, we want to provide or we want to evaluate the response character, response of the system, charge current, charge response, spin response in response to weak or even strong field. And by using this tool, we have investigated the optical photocurrent responses such as net. Okay, thank you for your attention.
Are there any questions or comments?
classical one. What is common between the Khiva approach, Khiva theory, and the nonlinear response theory? I mean, they deal with, one deals with quantum systems, and another one with classical, right?
Let me say that this response coefficient, the chi1 and the chi2, can be chi1 can be evaluated by the Khiva formula. Chi2 also can be written in terms of wave function, variance and wave function connection method.
Just some mathematical common feature, not physical, right? Because this is for classical systems. This is classical process, right? Nonlinear optics is classical system. But Khiva, for example, when you apply it to some solid state, some nanostructures, it is purely quantum systems. And then there are different responses. So can we say that for quantum we deal with linear response, for optical we deal with non-linear response?
Yeah. Let me say that we are totally working on the quantum mechanical system, and so the dipole polarization P, actually the change in the polarization can be calculated by using the wave function.
The dipole moment actually can be translated both in classical and quantum ones. In classical, you put this into the Maxwell equations. In classical, in nonlinear optics, right? You put them into the Maxwell equation for the medium, and then obtain different nonlinear wave equation. For quantum, it should provide some high harmonic generation. Is that true? For example, for quantum, you have to put that into the Schrödinger equation.
Yeah.
I see.
Yeah. So the thing is that let me respond this way. For example, yeah, this is the 2000 paper at SciPad. He wrote everything in terms of the second order perturbation theory.
So this concerns nonlinear response theory in quantum systems.
Quantum systems. Thank you. And what we are doing is that let's go to the first page 1. I can give my talk in just 1 minute. What? Yeah. So the SciPad is very great, very excellent paper, physical review in 2000. Everything in his paper is a second order perturbation theory, and one may question what would be the validity of the second order perturbation theory. But in our real-time calculation, we don't care about second order perturbation theory. We are proud that we wanna directly integrate in real-time integration means we include every order, not only second order.
Further questions, and then let's closing this session. Okay, thank you. Okay, we will have a coffee break until 30 minutes, so 4:40 we can continue in the last talk. Okay.
Thank you.